Graham Finch is actually a building science researcher and engineer with RDH Building Engineering. He's got a master's degree and investigated the field performance of rain screen walls and airtightness of multi-unit residential buildings in coastal BC. And this led to many publications and practical recommendations for the construction industry, a very hot topic here in BC. His work includes new construction design, hygrothermal modeling, forensic investigation, energy upgrades, whole building monitoring, several research industry studies. Graham's current project and research focuses on improving the energy efficiency of new and existing buildings through the building enclosure. Graham also teaches courses at BCIT, 2 courses actually, in building sciences on a part-time basis.
Good morning, everyone. How's everyone doing today? So how many of you guys have this book? Good. So those who have it are curious what's in it, or maybe those who don't are curious what is covered. Today, I'm going to talk about this new wood frame guide, what's in it, what it's all about, what the changes have been made since the previous best practice guides. I'm going to talk, if I have time at the end, about applying the guide and some of the educational initiatives we're doing to educate the industry, students, architects, contractors on how to build better buildings. And I'll touch on briefly an upcoming energy efficiency or building enclosure design guide, which basically takes this guide and takes the next step further to go towards highly insulated, more highly insulated enclosure assemblies. So this guide is an update of the 1999 and 2001 CMHC Best Practices Guide. The Best Practices Guide, as you know, came out of the leaky condo crisis. They culminated the research and the best practices at the time, so we'd make sure we stopped building buildings that were leaking. And the emphasis on these guides was on moisture control on our wet West Coast. The new guide is actually a publication of the Homeowner Protection Office, the branch of BC Housing. They've taken over the reins now from CMHC in publishing this new guide. Why we need a guide? You know, thinking back to 1999, 2001, before that even, you know, mid-1990s, we had a whole lot of problems with buildings. And for those who weren't here, if you Google leaky condo crisis, you'll find a whole bunch of information about buildings that were falling apart, rotting, decaying, in the sort of picture shown here. Even today, we're still seeing problems with buildings, moisture issues, moisture ingress issues that are still not being addressed properly. So the intention of this guide is to help builders and designers and architects design better buildings so we don't have these problems, you know, anymore. So what's in this guide? We talk about behavior of wood in construction, talk about heat, air, and moisture control principles, energy efficiency, so R values, code compliance, talk about building enclosure assemblies, so we'll talk about what type of wall, roof, below grade assemblies work, details for those assemblies, especially around window details and interface penetrations. And there's a discussion, a couple chapters on components and materials, and maintenance and renewal considerations. What's new? Well, much of this guide was updated on the premise of 5- and 6-story wood frame construction. So this guide takes into the principles of designing to higher wood frame structures and applies it in a lot of the details and the considerations you need to take into account. Of course, since early 2000s, there's been many code changes, especially City of Vancouver and BC with energy efficiency. And there's been a lot of research done in our industry to make sure our buildings work and follow up with the leaky condo issues to make sure that we don't have problems occurring again. There's in the National Building Code and the BC Building Code, you'll notice something called the Moisture Index. That's been integrated into this guide. There's also been a fair amount of work on rain screen monitoring and drying of wall assemblies, various new wood products, especially treated wood, and the industry experience as a whole sort of went into this to update this. There's also a greater discussion of the enclosure and the HVAC interaction of the building enclosure and mechanical systems, and improved energy discussion and guidance, particularly related to ASHRAE 90.1, which is applicable to 5- and 6-story wood frame. More detailed information related to windows, and of course, more 2D and 3D details up with current technology. So the first sort of topic that's talked about is the behavior of wood frame in construction. Everyone thinks of 5- and 6-story wood frame, and they wonder, well, wood shrinks, what's going to happen to my building, especially 6 stories now? And I know the issues I have in 4 stories are going to be exaggerated, right? So there's discussion around why shrinkage occurs, how it occurs in wood, how it affects different wood cuts, and how to potentially address it in your details. Another part of research that was done in the last 10 years or so was looking at average moisture, typical moisture contents that exist in rain screen walls and assemblies that are exposed in our climate. And the graph on the right here, you can see the months of the year, and you can see typical sheathing or wood sheathing moisture content levels based on outdoor humidity levels in Vancouver. And why this matters is because, well, if your wood's going to be going up and down with humidity in terms of its moisture content, but also if you're, say, investigating a building at a certain time of year, and you measure moisture content at 20%, that's probably fine in the winter time, but in the summertime, there's probably something going on there that you need to look into a bit further. Shrinkage. As you know, shrinkage is dependent on the amount of wood that you have, or the amount of wood that you have cross-grained to the wood, and the initial moisture content of that wood. So when you look at a building and you build it, what shrinks is all your floor joists, your sill plates, your top plates, essentially these components around here. So at each floor, we see a fair amount of shrinkage in that, say, 15, 16 inches of wood. And it can be in the order of, 3, 6%, which can, over 6 stories, add up. If you have brick cladding, if you have balconies, if you have other adjoining structures next to the building, that differential shrinkage needs to be accommodated, otherwise you end up with issues. So going from 2 to 4 to now 6 stories, that shrinkage is even more further exaggerated. So for example, in the guide it provides some cases for the amount of shrinkage. In the case 1 here, green, it's basically 30% moisture content, or where wood has got wet on the construction site. That never happens, right? And you can see a cumulative shrinkage of 5 3/4 of an inch at the top of the building. So if you have an elevator core out of concrete and your wood frame structure shrinks relative to that concrete, you have a 5 3/4 step to get from the top elevator down onto the floor. Mitigation measures can be done to make sure the wood stays dry during construction, seasonal time of construction, and you can get the shrinkage down to an inch to 3 inches or so. But it's a consideration that needs to be taken into account with the 6-story wood frame building. An example of this is where you have, say, brick veneer and stucco here, this interface detail, and this is, a building. It's only a 4-story building in this case. But you can see here how the flashing was poorly designed, and it acted now like a gutter to funnel all that water into that wall assembly and cause all sorts of problems. So when you're designing a building and you've got brick and you've got wood siding or stucco, thinking about how you would maybe design that flashing to allow that shrinkage to occur. One of the things that we presented in this guide, there was a lot of input into putting this together from APEG, AIBC, a number of professionals in the industry, including fire code consultants. And it was, well, how do we deal with these firewalls and these concrete elements and differential shrinkage related wood related to concrete? Well, one of the ideas proposed by the committee is, well, let's build a wood firewall, whether it be solid wood or framed wood, and use 2 layers of gypsum on both sides, and then have breakaway clips, and essentially design this so this can act within the structure. Some people have taken this approach, others don't like this approach, and as a result, FP Innovations is actually doing testing right now to show this actually can work and help the industry out and prove that a detail like this can work in an all-wood building, and you don't need to use concrete blocks. So stay tuned. This detail has created a bit of discussion in the industry, which has prompted the wood industry to act on its behalf. Integral to building science is heat, air, and moisture control principles. When we're thinking about designing buildings in our West Coast, we need to think about the exterior and the interior environments. So on the graphs here, you're seeing the exterior climate for Prince George versus Vancouver. And you can see the hours of sunshine in the yellow bars, and you can see the precipitation in the blue bars. And Vancouver, right like today, we're starting to get our rainy season, which will occur right all the way through to March. Whereas Prince George is getting a lot of snow, maybe in a few weeks, maybe even now. And they don't get a lot of precipitation in the winter. So our coastal climate versus our interior climates have very different considerations for rainfall and rain penetration detailing, but also the humidity and the other conditions that impact our buildings. So when we're designing walls and roofs, we need to balance the wetting versus the drying ability, knowing that the atmospheric humidity is pretty high and there's a potential for leaks. So can we balance the drying of our assemblies out versus the amount of wetting that gets in? So strategies to reduce the wetting, first of all, but also secondly, to make sure the water does get in, can dry out, which was one of the biggest problems with the leaky condos. Heat flow is integral to this. As we add more insulation to buildings, the amount of heat flow is reduced to dry out the potentially wet in building enclosure assemblies. So more energy efficient assemblies tend to use insulation a bit differently on the exterior of the structure to keep that structure warm. If we put all the insulation on the inside, you can end up with really cold exterior surfaces which are prone to damage. Water penetration, really a detailing issue, flashings and penetrations and assemblies and interface details. Airflow is very important. Air leakage, it's really interesting. You know, after fixing a lot of buildings, we're seeing a lot of air leakage issues that maybe were missed, or address a lot of the water issues, but airflow and condensation result. Air leakage, even in Vancouver, can cause problems, not only from condensation and damage, but from an energy standpoint. Controlling condensation and also addressing construction moisture. Another critical side of building science is the interaction of the mechanical systems with the building enclosure itself. And a classic example of this is an old leaky house. It's very drafty. The humidity is very low, and it's okay in the wintertime. It's not super comfortable. Versus a highly insulated or more highly insulated multifamily building, maybe where you have social housing or you have multiple people in the units. You add more people, you add more moisture, the humidity levels go up, the air tightness is fairly high, so you end up with all sorts of condensation problems. So interaction of airflow within buildings, so ventilation within multifamily buildings isn't great. There's been efforts recently to improve that. But in taking into account and controlling or managing stack effect, wind, and the HVAC systems. The impact of this interior environment on relative humidity levels, indoor air quality, and other things like architectural and space layout. That's simple things like putting closets on exterior walls, which are cold spaces, and you can end up with condensation inside. And also placing heaters on exterior walls where you maybe place a couch or something like that, and reducing the impact of that. Compartmentalization is the idea that you air seal floors and compartmentalize suites from each other. This is better done in concrete buildings, in wood frame buildings, especially in floor slabs where you don't have concrete topping, making that airtight so you don't have the moisture, or the air coming through there. It can be difficult, but it needs to be considered. There's a bit of discussion around HVAC systems, in-suite versus corridor systems. Most of our multifamily buildings are heated with electric baseboards or some sort of other, maybe hydronic in-suite. And there's a corridor pressurization system providing ventilation air. More current designs maybe integrate an HRV or some sort of in-suite ventilation system and not relying on the pressurized corridor approach. Other thoughts like placing furniture against your heaters on exterior walls, closets and exterior walls. And occupant use is always that wild card. So trying to design so the occupant can't actually mess it up. And where this sort of comes into play is, well, if you do have a couch on an exterior wall, that's a whole lot of insulation, right? If you place that right against your exterior wall or a bed or a couch, you'll end up with all sorts of problems in that wall or on the surface of that wall. It needs to be addressed. So designing the space so you don't have that is an important consideration. In terms of wetting and drying and that moisture balance, we need to take into account the wetting sources and then the drying mechanisms on the same side. Wetting, we have precipitation, we have water that's built in, we have vapor diffusion, we have air leakage moving moisture, we have groundwater. Drying mechanisms, with rain screen designs, we have drainage of water behind that cavity, behind the cladding. We also have airflow in there which acts to ventilate and pull away that moisture, and that's probably one of the most critical factors in rain screen design is that ventilation drying out that wood. We also have vapor diffusion and air leakage, which can also lead to drying as well. Heat flow is a big discussion in this guide. There's a lot of talk around R values, effective R values, compliance with codes. So there's a bit of a primer on heat flow mechanisms being convection, radiation, conduction, addressing those separate heat flow issues in a building design. There's quite a few tables and guidance and extra references to effective R values of wood frame enclosure assemblies. And this all ties into the energy efficiency requirements, and also the assemblies and details take these into consideration. So when you're trying to build a highly insulated building, you're not shoving in, structural penetrations all the way through the wood, and you're thinking of some way to address some of those unique details. In terms of water penetration control, this graphic sort of shows two different types. Historically, we built face seal stucco, or concealed barrier type systems. We also built mass and storage type structures where you have old historic masonry buildings. And a more modern, it's been around for a long time, but the common approach is to start building more drained and screen type cladding assemblies. And these drained or screen type assemblies can be vented, ventilated, or ventilated and pressure moderated. Most of our walls fall into that vented or ventilated, and we're aiming for that ventilated. And pressure moderation, especially in a wood frame building, isn't always necessary or even practical to achieve. So with that in mind, it's addressing the assemblies and also through all the details. So if you have a rain screen wall, the way you install your window, the way you detail that deck, the rain screen concept applies through all of those details. It's not just about adding strapping to the wall, it's about integrating that window in properly therefore it can drain out and vent out as well. In the first guide, there was the idea of what's called an exposure nomograph. And this is essentially a simple chart where you can look at the overhang ratio and the terrain you're in, and you can assess the exposure category. In this guide, we've added the moisture index. You can see by the numbers on the bottom here. And so what you can essentially do with this nomograph is figure out what your overhang ratio is, say for this window here, and figure out your terrain, whether you're exposed, rural, suburban, or built-up urban area. You can draw a line, and depending on the moisture index area you're in, and so Vancouver would be greater than 1, you can determine that that particular window or that particular door, maybe on a balcony or something like that, is in a pretty exposed location. So therefore, my detailing considerations would be a little bit greater than, say, if it was an exposed location. And that's important because, there's a lot of houses that people are adding 6-foot overhangs, balconies, verandas, and the way you detail that window under the veranda can be different than the way you detail it on the rest of the building, maybe the south face that gets all the rain. Airflow control. Airflow control is very important for condensation and energy efficiency. As we go to 5- and 6-story wood frame buildings, it becomes harder and harder to make current practices work. 5- and 6-story means a 10% increase in order of magnitude of wind loads. This may not seem a lot, but we're already pushing the limit with 4-story and using polyethylene as an air barrier there as well. So while polyethylene is still covered in this guide, there are alternate approaches to air barrier strategies and air barrier systems. Exterior sheathing membrane is becoming a very common approach where you use either a adhered or a non-adhered sheet type membrane, Tyvek, Typar, and it's taped and sealed, and then the strapping sort of holds it in place on the exterior with in addition to the cap staples. You can also seal the sheathing itself, and these approaches aren't necessarily all covered in here, but they're discussed in how you could apply different strategies into the details. In terms of condensation control, you need to control vapor diffusion, air leakage, and then surface condensation. Vapor diffusion, we use vapor barriers. It's a material placed usually on the warm side of our insulation. In terms of air leakage, it's a system that we're designing, we're detailing, so we can control the airflow through our assemblies and details. And you also can get condensation on surfaces, like windows are a very common location of condensation in your house. And in terms of surface condensation, it's maintaining indoor surface temperatures above the indoor air dew point temperature. That's not always possible to do, especially on windows, but there are strategies in talking about how the indoor environment impacts that condition. In terms of the energy efficiency requirements, there have been a number, and you guys have probably been hearing nothing but ASHRAE, and I've talked about ASHRAE before, what BC is doing, what City of Vancouver is doing. This guide will help you navigate through those codes and the upcoming changes. This essentially, it talks about the 2006 BC Building Code, but all the same information can be applied to whatever happens in the future and in the city and Vancouver as well. In the guide, there's a number of different wall assemblies than an usual 2x6 wall with bats. We talk about exterior insulated, we talk about split insulated, and the effective R values of those assemblies, and how those walls and the windows and roofs and all these things can be traded off with each other in terms of a whole building energy analysis. In terms of energy, it is complicated. I wouldn't expect you to squint and read all the things on here, but really what divides the energy efficiency requirements is Part 3 to Part 9, and a high-rise versus a low-rise building. High-rise being greater than 5 stories, or greater or equal than 5 stories, and low-rise being less than 5 stories. And depending on if you're Part 9 or Part 3, Part 9 you're using a prescriptive table, so anything 4 stories or less is typically going Part 9 prescriptive, and you're all pretty familiar with that in Part 10. But high-rise construction, which is a 5 and 6 story wood frame, will actually have to fall under ASHRAE 90.1. And then what version of ASHRAE you use depends on which area of the province you're in. If you're in Vancouver, it's 2007, and the rest of BC is 2004. And within ASHRAE, there's different compliance paths. There's prescriptive tables, there's energy cost budget, there's building enclosure trade-off paths, which you can use to make the building comply. There's a bit of guidance to talk about how those paths work. In terms of windows, so we got insulation for walls and roofs and assemblies in one part of the code. Windows have partially been taken out of they've never really been in code from a performance standpoint. And that's where the Energy Efficiency Act came in a number of years ago and mandated requirements for the sale of windows. There's legislation around the sale of windows that you can't sell a window into a building that has a U value greater than a certain number. And for Part 9 or 4-story or less building, that U value is 0.35 imperial or U of 2. So there's a number of windows that you may have been using in the past that can no longer be used because of that Energy Efficiency Act requirement. If you're doing in a high-rise building, you can trade off the windows. You can use lower quality windows if you use better quality walls, and there's some vice versa to the trading, although there's only limits to how much wall you can trade off with windows. So the guide talks about the roadmap. There's also an HPO bulletin on this on HPO's website that talks about fenestration requirements in BC. You're all familiar with this table in Part 9. This is the BC Part 9 table, which is now in Part 10 of the BC Building Code. That outlines prescriptive R values for assemblies. These are nominal R values. These don't take into account thermal bridging through wood, fasteners, penetrations, things like that. But we've been building R20 bats within 2x6 wall for a long time. And if you start looking at where ASHRAE is and where future code requirements are going, it's much higher than this, and it's also taking into consideration effective R values. So to get you ready for effective R values, there's a whole bunch of discussion around that. In terms of ASHRAE 90.1, I could talk for 3 hours and plus on ASHRAE 90.1. It's not a super exciting topic, but it is something that is prevalent in our industry now, and people are concerned about and interested about, and well, how do I make my building comply? You probably share some confusion as to the HJs and many other in our industry. There are 2 versions of ASHRAE 90.1 that are currently referenced in our building codes, 2004 and 2007 version of that standard. They have this very similar requirements. They're slightly different tables, and they have the same trade-off paths. When the ASHRAE 90.1 2010, which is the current one, gets adopted by, say, the city and the province at some time in the future or whatever version, it's just about changing those R value tables, which is fairly easy to do and update the guide. So when that happens, we'll probably have updated pages for the guide as well. The interesting about ASHRAE is it actually breaks the province of BC down into different climate zones than you're familiar with in Part 9. So it breaks it down on 1,000 scale heating degree days. We're climate zone 5. Interestingly, because of climate change and other things, Vancouver has actually crept into climate zone 4, like Seattle and Victoria over the last couple of years, and who knows when they'll update the climate zone recognition in there. But we're still climate zone 5 now. In terms of climate zone 5 or other requirements in BC, we have all climate zones 5, 6, 7, and 8. The requirements for wood frame walls in 5- and 6-story wood frame buildings or any building falling under Part 3, so you could have a 4-story falling under Part 3. In Vancouver, it's actually only R11 effective, which means you only need to put an R13 bath. So you can actually do a 2x4 wall in the city Burnaby if it's complying under ASHRAE, where if it's Part 9, you'd have to stuff in R20 baths. So there's little things like that, and that's why the provinces and others are trying to get up to the current standard, which is around an R19 effective. You look at Zone 7, you see R19.6 effective right here, or RSI 3.45. That doesn't mean R20 baths. That means R20 baths plus something else, or R2x4 plus something else. So in the guide, we talk about what are the effective R values and how do we get to these higher, highly insulated assemblies. What matters? Framing factors. How much wood? You got studs at 2x6, or sorry, at 16 inches on center or 24 inches on center. Do you have any steel in there? And there's this thing called continuous insulation. And continuous insulation is insulation that's installed exterior or interior of the structure that is continuous except for fasteners and other sort of mechanical penetrations. But you do have to account for framing and if you had girts or something like that in there. So if you look at prescriptive paths for walls being 19.6 effective, 2x6 wall right now with R19 or R21 bats, even R30 is still going to be well below that requirement of 19.6. And the way to get there is to add insulation on the exterior assemblies. What type of insulation, how much, and that's the big discussion. That's sort of where we're headed. Interestingly, in Vancouver right now, which is ASHRAE 90.1 2007, already requires 19.6 effective, and the only way to get there, maybe a 2x4 wall with R8 on the outside, or a 2x6 wall with R5 on the outside, or 4 is even sufficient. Another consideration, and looking at a lot of buildings, 5- and 6-story buildings that have been built in similar seismic zones, Seattle and Portland to a lesser extent, there's a whole lot of wood in these exterior walls. There's a lot of structural requirements, especially where you got a lot of glazing areas, you have a lot of hold downs, tie downs, and smaller shear walls. So when you look at a wall like this, and you got to put in 19.6 effective, where are you going to put that insulation? There's no space anymore, and cramming it in between that threaded rod there is really not going to help you a whole lot. So there's all sorts of surface penetrations, ducts, things that are running through the wall, and those things are all more limited. So thinking about this, it may, on initial design, well, I'm going to put R20 in the wall and something on the outside, or you're just going to rely on the R20. If you actually don't have the space for it, you can't meet the ASHRAE requirements. So it makes it a little tricky. And then, if you get to the point where you're going to start insulating the building, you look at the building like this, you're like, well, how am I going to comply with code, and how am I going to sign off on this building? Well, that's where exterior insulation and alternate approaches, and unfortunately, late in construction, that can really hurt you. In terms of windows, we've got vinyl, fiberglass, wood, aluminum windows. We got different types of clad windows. ASHRAE 90.1 2007 differentiates between window frame types. So if you have a vinyl window versus aluminum window, there's a different requirement for the U value you can put in. ASHRAE 90.1 and the Energy Efficiency Act require what's called NFRC certification, which is the National Fenestration Rating Council. And what they do is they look at everyone's window with the same program or the same sort of analysis, and they determine what the R value or the U value for that window is, the frame, and all the things. With ASHRAE, and it's usually not a huge problem with wood frame building, it's more of an issue with concrete buildings, is there's a maximum glazing ratio that you can have, with being 40% or 50% in 2004 and 40% in 2007 version of ASHRAE, where you then have to put in, then you have to go to a different compliance path. So you can't use the prescriptive path, which is easy if you have greater than 50 or 40% windows, which adds a little complication if you want to use the trade-off paths. In terms of windows and why are they so important, and we do talk about them in the guide. A few of you may have seen a similar type chart before. If you look at, well, what's the impact of putting an R2 window or a window in a wall, and what's the impact of that window on the overall effective R value of my building? If I have R 16.9 walls, which are 2x6 wood frame with R21 bats, I get R 16.9 if I have no windows in that wall. If I have 100% windows at R2, the overall R value is going to be R2. Okay? The tricky part is, well, between that 100% wall and 100% window case, you have this scale. And it falls on the depreciating returns because it's, the heat flow is proportional to U, the U value, which is inverse of the R value. And what you can see on the chart is, well, very quickly, by adding any amount of windows to that wall, I very quickly decrease the overall R value of that assembly. So when I had R 16.9 walls and I had 40% glazing area, the effective R value is R 4.25. And so in terms of input into energy models or trade-off paths, that's the R value you have. And you can see here going down into, that's not my phone. Oh, sorry, I thought it was a computer. Anyhow, you know, and going up to 50%, you go down further in R values, and all the way down, you know, and higher glazing ratios, obviously lower. What you can do with this information is you can do some simple trade-offs. So if I want to design an energy efficient building, if I want to design a more efficient building, or if I'm trying to just meet code, I can assess the heat flow through my different components. And there's guidance talking about how you would do a simple trade-off and how you would analyze your building to assess the heat flow paths. So if I got all R20 walls, R2 windows, and R40 attic, you do what's called U times A calculation. It's the area weighted heat flow calculation. And you do this little calculation, as talked about in the guide, and you determine that 83% of the heat flow in that U times A is actually through your windows. So R20 walls, do I really care? No, I need to maybe address something that actually influences the overall factor. So while we talk about highly insulated walls and roofs and other things, often it's the windows that you can play around with and use better windows to actually make some of these trade-offs happen. So if you're really concerned about getting R19.6 effective in your walls and exterior insulation, just tweaking the windows and using better windows can actually help you meet those code requirements. So in this particular case here, windows at 28% of the area represent 83% of the thermal losses. That's pretty high, right? So if you see a number like that, and why we point this out is so you can address the things that matter. If I were to stuff in R60 into that attic, that's something that only has a weight of 4%. It makes pretty much no difference to the overall R value and the heat loss of that building. In terms of trade-offs, this is where you can play around. You set up a little table, and you can see here if you go to like a triple glazed window in low conductivity frames, you can get up to R5.9 pretty easily. The cost isn't that significant. Cost from double to triple, a couple bucks a square foot. And looking at this from a standpoint, you got windows now 63% weight, and the weight of that wall is much higher, and the overall R value is now like 13. And what's interesting is, and it's because you're dealing with addressing your worst links, is if you address those weakest links, you can actually make the biggest impact. So changing from R2 to R5.9 increases the overall R value of the building by 122% and reduces your heat flow by 55%. So seemingly small changes at bad details and bad assemblies can actually make the biggest difference. And so with that in mind, going through the design of your building, it's fairly important from an energy efficiency standpoint. The next chapter in the guide talks about assemblies. Talk about different types of assemblies. They're considered best practice for walls above and below grade, roofs, decks, windows, and balconies and walkways. With each of the details, there's a discussion of critical barriers. What critical barriers are key elements in your design or your assembly that have a profound impact on the performance and the durability. The water shedding surface, your cladding, your flashings. The water resistant barrier, usually your sheathing membrane or some innermost plane where water can safely get to and drain and dry out. The air barrier, and then the vapor retarder. And with each of these assemblies, there's what's called factors limiting performance. So thinking about, well, if I build this rain screen wall here, or if I build in this climate, what may impact that overall design? So for below grade walls, this is a wood frame guide, but there is a discussion around concrete below grade assemblies, whether you use exterior or interior insulation. So each of these tables, essentially, in these one-page discussions, just like the old best practice guides, presents a thumbnail of the assembly, what it includes, and it talks about the water shedding surface, the WRB, the air barrier, the application, and the factors limiting performance. Cautionary remarks about adding bat, on the inside of concrete walls, because we know that doesn't work all that well, even though it may meet the energy code requirements. Above grade walls, this is where it gets more interesting. 5- and 6-story wood frame buildings require the use of non-combustible cladding. So you're not putting vinyl siding up on 5 to 6 stories. Air barrier strategies and split insulation. So we do talk about different insulation strategies and what are the different critical components of that wall, and what are the factors limiting performance, and what insulation maybe is better to select over another type. Roofs. There's been a lot of, say, progress in roofs, especially in terms of spray foam. A lot of people want to put spray foam on the underside of decks and make unvented roofs. There are issues with this, especially if your water shedding and your air barrier and other interfaces aren't dealt with properly. So there are discussions about the application of the risk of certain assemblies and where one may be more appropriate than another. A vented roof is still safer than an unvented roof in most scenarios, unless, of course, you can't get that unvented roof to work properly. So there's a discussion around that particular aspect, especially regarding spray foam right now. In terms of windows, how to evaluate window frames, there's hundreds of manufacturers, fabricators of windows. How do you evaluate the frame for rain screen performance? Are they appropriate for our climate and exposure? Does the window frame you're using, does it make sense to use that in a 6-story wood frame building? There are a lot of window frames that are not suitable for use on 5 and 6-story because of the increased exposure. They will leak. So in terms of the details, there's 31 plus details. Each of those 31 details, there's 1 or 2 iterations showing different materials and different assemblies or different strategies for air tightness. They are illustrative to provide fundamental detailing concepts. They're not the definitive solution. You don't have to follow. This is not the Bible of building science in BC. It provides guidance, and it gives you an idea of what is important. But if you don't want to design it that way it's detailed in there are many alternate approaches. We've gone into the detailing. Water shedding surface, so that's water deflection away from the cladding, flashings. The value of overhangs, drip edges, things that deflect the water away and manage the surface water. The amount of water running down a 4-story versus 6-story is obviously increased in that 6-story. By the time you get to the bottom of a 6-story wood frame building, there's a lot more water down there to address. And so appropriate use of flashing and membranes and termite control is also covered. In the detailing considerations, there's a discussion around the appropriate use of flashing membranes. Too much vapor impermeable membrane, like in this picture, on the exterior can lead to increased condensation potential and reduced drying and end up damaging your building. So this approach where you just splatter the building with peel and stick is not the correct approach to dealing with water. So more appropriate strategies and more appropriate use of expensive but also impermeable membranes can also be addressed. The details, the use of color. The old guy was black and white. This one's all color. And so you can see the details here. The critical barrier discussion, there's green, red, and blue lines identifying the water shedding surface, the WRB, and then the air barrier. And then a color detail which labels and notes every possible material in there so you can actually build this. Okay, so this is done for key details on any wood frame building, applicable for multifamily, applicable to a house, applicable to even to commercial buildings and other types where you have the same sort of considerations. One of the details that's covered new in this guide is the use of split insulation. This is where you have insulation inside the stud cavity and on the exterior, whether it be rigid mineral fiber, rigid fiberglass, or even foam in some climates. And there's discussion around the appropriateness of different types of insulation, depending on your split. With this approach, the air barrier is the sheathing membrane behind that insulation, and then detailing, therefore, follows from that. In terms of meeting future and even current energy code requirements, this type of assembly is looking like it's going to be the way things go in a lot of cases. There are obviously going to be multiple different ways you can build a wall, but in terms of cost effectiveness and ease of construction, the split insulation for wood frame makes a lot of sense. In terms of accommodating shrinkage, if you have brick, veneer, and a tall wood frame building, the window details and other interface details are addressed and talked about. Well, how can you address the shrinkage of that wood frame relative to the brick so your window flashings aren't, creating gutters at every windowsill. There are a few details in 3D. So our balcony interface here with guardrail. You can see here, and it sort of goes through a four-dimensional, let's say, where it's 3D with the application of sequencing to help out with some of these key details here. This is done for a balcony interface, and it's also done for windows as well. The last couple chapters talks about selection and specification of products. Wood, specifically related to treated wood and other types of wood, appropriateness and different treatments. Insulation, sheathing membranes, flashing materials, aluminum and galvanized, eaves trough and rainwater leaders, metals there, cladding types, combustibility considerations for taller buildings, windows, skylights, doors, sealants. Sealants are very important. If you're using a not-so-great sealant on the 6th story, you're not going up there with a ladder to fix it, so consideration of better use of products when you're getting into these taller buildings that are harder to access. Paints, exterior coatings, likewise, similar considerations as well. Water-shedding roofing and waterproof roofs, so essentially an inverted or a conventional type of roofs or sloped roofs. And then talking about PVC, urethane, and different balcony and walkway membranes that may be used. One of the key things, and maybe overlooked, in especially the design, if you take a 4-story building with a nice roof line and bring it up to 6 stories, accessing those areas of the upper part of the buildings can become very difficult. In a high-rise building, we're used to using bosun chairs, but accessing this, the building on the top right there with a bosun chair would be very problematic. So the use of boom lifts can be a consideration, but then obviously design of that podium area around your building to be able to access the building with boom lifts is another consideration. Takes away a lot of the fun, but unfortunately it needs to be considered. You can't use a ladder anymore. I don't know anyone that wants to go up a 6-story building on a ladder. That would be pretty fun, right? Bosun chair may be an option, and that for a flat roof building, that could be your strategy to address and do maintenance on these buildings. So a bit of time left, so I'm going to talk about how the guide is being used and just maybe some more information. If you're keen on getting more information about building science and detailing, myself and others teach a number of classes at BCIT. One's BLDC 3050. It's an introduction to building science and building enclosures. It's theory and fundamentals. And this guide is used throughout the course to help students out with understanding building science in BC and application of fundamentals and principles into design and detailing. A class that we just started up 8 months ago is BLDC 3060, which is building enclosure detailing. This is where we actually have 2 teaching huts where we take the details in these guide and we actually build them. The students are about 20 students, 25 students per term, and they build these details and they go through the guide and get some education on that. So the teaching huts, they're modular, they're small, obviously you don't have a lot of space, but you're allowed to plug and play balconies, doors, and windows, and different interface details, roof wall interfaces, all the details in here I want to talk about and sort of go through how you would actually achieve that. You can see here a student doing a vent detail out of the guide, application, maintaining that air seal, and when you actually see these details, it's great. The guide shows you, these great details, but actually seeing it in physically, and if you don't have maybe the chance to do this in your practice, then this is an opportunity to sort of learn. Window details. There's a lot of different window details in the industry. This guide presents a simple detail that can be done with anyone's sill membrane or flashing membranes. It doesn't require any proprietary products or sill pans. Obviously, there's a whole host of details on how you would detail the sill and how you detail the window frame going and opening. What this guide does is it goes through the fundamental concepts for maintaining window in proper installation, and then also so it maintain the rain screen principle all the way through that. And then split insulation, we also cover how you would do this and how you would attach cladding or potentially through a split insulated wall assembly. Another guide that's coming up is a high performance wood frame guide. So it's an energy efficient building enclosure guide. It takes what we've got in this guide, but it brings it to the next level. This brings you up to the levels of passive house. It would bring you to levels that would help you achieve net zero, and also even the next building code. If you look at the National Energy Code for Buildings in 2011, the R values and requirements in our colder zones are, R27 effective. That's not so easy to achieve anymore. So essentially, the guide is similar to this guide. It focuses on durability, air tightness, and energy efficiency, best practices to highly insulated wood frame assemblies. There's also quite a bit of discussion on CLT assemblies. So those who checked out their talks on cross-laminated timber or mass timber would appreciate some of the details that are in here, which maybe aren't necessarily covered in that guide. This guide is written for a North American audience. There's a couple different guides. The first one's going to be for climate zones 4 through 7, which is sort of our climate zone, the coast and everywhere else. There's ASHRAE 9.1, the National Energy Code for Buildings. There's NBC 2012, IECC, which is in the US. There's a whole bunch of green programs. So there's a whole chapter to essentially figuring out all these energy codes depending on where you are. So if you're in Edmonton, or if you're in Calgary or Vancouver, you'll be able to go through, figure out what climate zone you're in, and figure out what R value requirements you need for different components. Highly insulated assemblies, we've got split insulated, we've got double stud, which is talked about. Double stud can also represent deeply insulated walls, something passive house design with 2x10s or something like that, and cross-laminated timber. Considerations for more highly insulated assemblies: as we add more insulation, we potentially have a higher risk of moisture damage. And the reason we do is because we're reducing the heat flow through that wall or the roof that may have dried it out before. Now that's no longer there with R60 in the roofs or R40 in the walls. So if you can't just take the same practices you've been doing for a 2x6 wall and apply it to a double stud. Some of the detailing and other considerations, especially with air tightness, become very important. We're seeing people in different areas, North America, trying different things out, and some work and some don't. And this guide sort of culminates a lot of that evidence and that discussion. One of the big things that there's been a lot of research on lately is how do you attach cladding through exterior insulation? There's an alternate number of approaches. You can use screws through the insulation, and that works from a structural standpoint. There's also clips and shear blocks and all sorts of different approaches that if you're putting on the insulation on the outside, you're no longer bridging all that insulation with framing, specialty steel or something like that. Again, details here, you can see it covers a number of details, typical details here. And you can see, well, what happens, in the same details we talked about in the other guide. Well, how are you going to maintain air barrier continuity through maybe a split insulated wall with a lot of insulation into that highly insulated roof? 2D and 3D sequence, there's a bunch of window build slides because we find some of these are more critical, especially for teaching as well, for double stud, split insulated CLT. So that's the next step from this guide. Brings you to the next. And this is being published actually by FP Innovations, and it'll probably be ready sometime next year.
Who actually administers the Energy Efficiency Act, especially for windows?
The Energy Efficiency Act is actually legislation, so it's like a law in simple terms. And jokingly, there are window police, but they're essentially policing the manufacturers, right? So they know who the manufacturers are in BC or selling windows, and they're enforcing it from that side. The AHJs, the building officials, it's not necessarily in their mandate to do so. Building professionals, it's sort of like,
someone breaking the law on your building site, I mean, that's where the professionals are sort of brought into it a lot. Unfortunately. Yeah, and Energy Efficiency Act is actually just like buying a fridge. It's fairly easy to comply with. It's just a U value requirement, and if it's spec'd in on the job, and the windows, they have labeling requirements, and it's all in there.
All right then. Well, let's thank our speaker.